Okay, in today's presentation, we will look into these kind of illustrations. You can quickly note these things down. Again, maybe the first example what I am going to take here is somewhere a repeated one. You can see here LD X 400, then followed by out T 450, the second instruction, then K6, then you have LD T 450, then you have out Y 430, out Y 430. So, these are the 5 instructions, right, which are given as a problem statement, right. So, now you will have to devise the ladder diagram for devise the ladder diagrams for the instructions given. Devise the ladder diagram for the instruction given. This is a very simple example. You know what exactly this means after by looking at the program statement itself, I mean the instruction itself, you can say that 6 seconds after the input X 400 is activated, your output is going to be activated. That is the simple meaning of this particular set of instructions, because what you do here is if you draw the ladder here. So, LD X 400, so your X 400 would come here, then that will activate one output device. In this case, it is T 450, T 450 is the output device here with K, that is the setting of 6. So, this is my X 400. This example somewhere we have taken earlier also, but that time the problem statement was given and you were writing the instructions. Here the instructions are given, you are supposed to write the problem, the inference of these instructions, right. So, now we have come up to here, this is over, we have come up to here. Now, in the second rung, you know that whenever an LD instruction begins, it is understood that you have come to the next rung. So, LD T 450, so T 450 happens to be a switch now, which is actuated by means of your timer contacts T 450. Then this will lead to an output, that is Y 430, and you can have an end rung also here. This is how you have devised the ladder diagram, and you can always write the inference what exactly this ladder diagram does, right. An output Y 430 is actuated 6 seconds after there is an input which is indicated by X 430. So, this is what is one of such instructions which are given, and you will have to draw the ladder diagram. I hope all of you have noted these things down and taken it. And we will see one more similar example what we have seen just now, wherein we will have another set of instructions. Please note down. LD, again you begin with LD x 400. The first instruction is LD x 400. Then OR Y 430. OR Y 430. The next instruction is ANI T 450. ANI T 450. Then the next instruction is out. One second. ANI T 450. The next instruction is out Y 430. Out Y 430. Now the next instruction is LD X 401. By looking at these instructions only, you should be able to understand in what way you will be having your the ladder diagram. So X 401 is the next instruction. Then you have OR M100. Please recall what exactly we mean by M100. It is the internal relay bit, internal relay coil. And you have the next instruction as AND Y 430. Then you have out T 450. Out T 450. So whenever you have out, you should have an instruction with K10. You have K10 followed by out M100. So these are 4 plus 4 plus 2, 10 instructions given here. You are supposed to devise a ladder diagram for the set of instructions given. Devise a ladder diagram for the set of instructions given. So now on the same grounds of what we have seen in our previous example, let us try to draw the ladder diagram for this example as well. Now I would draw the rungs here, the power rails. So LD X 400. So now this happens to be my X 400 here, as you know. OR Y 430. So you have one parallel branch here. So this is my Y 430 here. Y 430. ANI T 450. So ANI. So whenever I mention about ANI, so this is a normally closed switch. So this is my T 450 here. The third one, it is T 450. Then out Y 430. So this is my Y 430 here. Y 430 in my which is my next element in the first rung. So in this way, the first rung, which has got 1, 2, 3, 4 elements, they are taken care of. 1, 2, 3, 4. So now whenever I have got an LD instruction, I would begin with the next rung, and again when I come here, I would start with LD X401. So X401 comes here, which is again in parallel with one more switch as per the output of an internal relay, that is M100, and now you have the next instruction as AND Y430. So I have to have Y430 here, then it will give me one output. In this case is the timer with a value of T450 and your K of 10, as you can see, T450, K of 10. Then out M100. So now when you have out M100, you will have M100 coming here only, because you have got two outs here. One is this and another is this. So both should come in parallel. So that means this is your M100. So this is what is the set of, the ladder diagram for the set of instructions given. Now you should be able to interpret what exactly happens here. So you will have to write in each step or in each rung what exactly happens, and in totality what exactly happens. Please note down the ladder diagram. Make sure that all the elements are covered here. Now here one important aspect to be noted is, whenever you have got a switch which is related to the output contacts coming in parallel with the input switch, that indicates your input switch is always a push button switch, momentary switch. That means when you press X400, momentarily your Y430 starts there, as you can see. Since Y430 starts, its contacts are connected in parallel with X400. Even though your X400 is removed, your Y430 will continue to operate. This is what we have seen in our earlier presentations also. This is one thing. So that's what happens even in this example, till you have the instructions out Y430, LDX400 or Y430, ANI, T450, and for the time being let us not worry what exactly your T450 does, because its contacts are somewhere later, right? Only the switch corresponding to its contact has been included in the first rung. That too, it is a normally closed switch. So in the first rung, it does not have any effect on the working of Y430. It will remain as a closed switch as long as it is interrupted by your T450 somewhere else in the program. So you will have the output Y430 getting activated by a momentary closure of X400. That's what is as far as the first rung is concerned. So then you have X401. So your Y430 will now continue to remain. So you can even have a kind of timing diagram here. That is also possible for you to have. I can have a small timing diagram also here. This is my momentary switch. This is my X400. Okay. So once your X400 starts, so your output Y430 also starts. How long? That is to be decided by the actions that are taking place in our subsequent runs. So now you have got X401 in the next run, X401. So X401 is in parallel with your M100. So for the time being, let us not worry what exactly is the position of M100, because I have to go across one or two more elements in that second rung. So now when I close, say, let us say that I close X400 somewhere here. That means this is the output here. This is X401. X401. Maybe it is also momentary. Whether it is momentary or not, that is to be decided by which element is across it in parallel. So now Y430 is already closed because this output is activated. So when this output is activated, this will now become normally closed switch, because earlier it was normally open. So X400 is closed here, sorry, X401 is closed, Y430 is closed. So that will activate your timer now. So X401 is here, Y430 is already in the closed position. Now the moment you come here, your timer T450 gets activated. T450 gets activated. So same output. Okay, so that means your M100 is also connected in parallel with T450. So your M1 activated here only. This is your M100. M100 is getting activated. So because M100 is getting activated, whether your 401 remains activated or not, that does not make any difference. So you can have your X400 also in the similar way, a momentary switch. So this is my X401. The sequence here, this instant is at your discretion, right? The closure of X401 momentarily, that is only to activate your timer. X401 is only to activate your timer. So now after 10 seconds, let us say that from here to here you have got 10-second timer. Okay, so up to here. So after 10 seconds, what happens here? Your Y430 will be now open, because this 250 will now get opened, because the timer has elapsed its time duration of 10 seconds. So T450 gets opened. The moment T450 gets opened, your Y430 will stop now. Once your Y430 stops, what happens here? Your timer is also, anyway, timer is already stopped here. So your M100 also is going to stop here at this instant. That is after a delay of say 10 seconds. So this is the 10-second delay, right? So now your Y430 would operate for a longer duration because the Y430's occurrence is as decided by X400, but Y430 will remain in operation 10 seconds after your X401 actuates. Is it so? Please think that your X400 will start, X400 will make your Y430 to start, so Y430 will begin. So now you can bring an analogy of some industrial process or something like that, right? So now you have turned on a motor to fill the water in an overhead tank, something like this, okay? So your Y430 you can consider it to be a motor, and your X400 you can consider to be the switch of that particular motor, right? So now you turn on the switch X400, your motor will start and water starts getting filled in the overhead tank. Now what exactly your X401 resembles here? I just draw it here. So now you have got a switch here. Okay, so this is
like this, right? Once the water one, once X401 activates, you will allow the motor to run for 10 more seconds so that the water may get filled up to the maximum level, something like this, right? And you can stop the motor. So that could be 10 seconds, that could be 1 second, that could be 100 seconds, that all depends upon what exactly are your practical needs. So now consider as one example, and you can just think of what is the significance of M100 here, right? So M100 as it is in the problem is not that significant. of one particular switch or an output device is concerned, your internal relays are not that significant. But whenever you want to have multiple controls, right, by means of a relay like operation, then your internal relays play a very important role. So here in this particular example, anyway it is present, the internal relay is present, but that is to maintain the working or the conduction of your timer T450, right? And even when the push button switch X401 is removed, that is the reason why your M100 is present there. So this is how you will have to interpret the instructions, and accordingly you will have to draw the ladder diagram. So in the examinations, the questions may be asked in different ways, because this is a very simple concept to understand, right? So you may be given the problem like this also, right? There is a switch which is to turn on the motor, which is used to fill the water in a overhead tank. So there is a water level indicator. After the water level indicator gives the output, after 10 seconds you have to turn off the motor, something like this, right? So if that is the question, then you will have to draw the same ladder diagram and the instructions here. But here in this example, you have been given the instructions and you will have to devise the ladder diagram, and you are supposed to write the inferences, right? So this is one more example which I wanted to take. So as long as the timers are concerned, I think we have taken several examples, right? So right from
the on delay timer, off delay timer, right? So maybe to turn on your slip ring induction motors, that example also we have taken, right? And like that we have taken some other industry related examples also, simple examples, but which shows the significance of your timers, right? So with that, let us move on to the next aspect, again equally important as the timer, that is the PLC counters. In the beginning only I have told you what is the difference between the timer and counter. So the timer operates based on the internal requirement in the sense the time delay. So between the two instances, what time delay you have to provide, that is as decided by the internal things of your PLC, whereas the counter has to count the external events, right? That example also I have given you in the beginning only. So there is a door, right? So maybe your cinema hall or something like that, which is having the capacity of say 100 seats. So every time a person enters, right? So you have a setting of 100. When the first person enters, it will become 99. When the second person enters, it will become 98, so on and so forth. When 100th person enters, automatically there should be a closure of the door, something like this, right? You have got the parking lots where you have got the parking capacity of say 20 vehicles, right? As and when the vehicles move in and move out, both are to be taken care of. When 4 vehicles move inside, there is a slot for 16 more vehicles, but out of that 4, 2 have gone out, then it should automatically show that there are the provisions for 18 vehicles, something like this, right? So all these are externally initiated activities, right? So you will have some external operation, maybe the arrival of the vehicles inside the parking lot, or it may be the rotation of a shaft, right? So how many rotations it has to do in a particular period of time, or it may be the most suitable example here would be packaging, right? You know what you mean by packaging, right? In the industrial process, right? So you have some beverages which are getting packaged, right? So they are all going to a particular set of crates. Let us say that there are 100, a particular crate has got the capacity of 100 bottles, right? So after the 100th bottle is packed or it is sealed, right? It is put into the crate. So there should be a deflecting mechanism which should take away the crate which is full, and it should make one more crate to come in. So that process might take some delay. After 100 bottles are filled up, you may have a small delay of 5 seconds before the next crate is positioned and the packaging starts. So there you may have to use the timer also, the counters as well as the timers. Many a times the timers and counters are used togetherly, but however you can always have the timers and counters used in a different context also, right? So let us look into what exactly we mean by PLC counters. So in this particular topic we will be discussing about the forms of the counters, how do you program the counters, then what do you mean by up counter and down counter, or up counting and down counting, then the example I just mentioned, the timers with counters. Then a very important thing is about the sequencer, right? So in the industrial process control and all, the sequencers play a very important role where the different events are to be properly sequenced, right? I will give you the example that time where how exactly we will be able to have the sequencing and the use of the counters and timers in the sequencing process, right? So now let us look into some of the basic aspects of these PLC counters. As you can see, these are too simple to understand, right? Counters are provided as built-in elements in the PLC and allow the number of occurrences of the input signals to be counted. This example I have already made a mention just now, right? They are provided as a built-in elements, right? So now after you see the microcontrollers and all, right? So you know what do you mean by microcontroller. The counters are also built in there, the timers also built in, the different ports are also built in, right? So your serial communication, UART, USART, many of the things are built in there. To some extent, memories are also built in. Like that, in the PLC, the counters are the built-in elements. What exactly they do is they allow the number of occurrences of input signals to be counted. So now there is an example here which I have already made a mention, where the items have to be counted as they pass along the conveyor belt, the bottles getting accommodated in your crates. Just now I have made a mention, or the number of a shaft, number of people passing through a door. All these examples I have made a mention. So in such circumstances or in such cases, you would be requiring the counters. So now, after having seen what exactly is the requirement to have the counters, let us try to see what are the different forms of counters. Now you can see a counter is set preset number value, and when this value of input pulses has been received, it will operate its contacts. I will show you the diagram. So the basic principle we have already seen on what principle your timer operates. There will be some contact, there will be timer coils, this kind of already taken, there will be some contacts, there will be some coils, right? So now this contact, say let us say that this is X400, this will activate the timer. So now depending upon the setting, say K5 or something like that. So this T450, what we have seen, that will actuate or that will activate some output which has Y430 or something like that, right? This is what we have seen as long as the timers are concerned. In the very similar manner, the counters also operate, right? They are set to some preset number of values. They are set to some preset number of values.
Actuation you want to have by means of the counters, you would either use a normally open contact or the normally closed contact. Now let's look into the meaning of the down counters and up counters. You can see here the down counters. Anyway, these are the very common things which you have probably already been familiar with, right? So the down counters count down from the preset value to 0. The example which I have already made a mention, that is there are 100 seats inside a cinema hall. You have the preset counter to 100. So once a particular person enters, whose entry is identified by means of some kind of pulse or some kind of change in the signal level or something like that. So what exactly happens is it starts counting down from the preset value to 0. That is, the points are subtracted from the set value. 100 minus 1, 100 minus 2, 100 minus 3, something like that. When it becomes 100 minus 100, that is when the count is the 0 value, its contacts change the state. So you actuate a door to be closed, or you make a motor to turn on,
you make the system to stop or system to start, something like that, right? So contacts change the state, that is to give some kind of output as required in the operation of the system, right? So as you can see here,
terminal count has reached 0, it is relatively simple to make the changes in the states of the contacts, right? However, that doesn't mean that you are not using the up counters. Up counters are also used, whereas you have got a preset value. The up counters count 0 up to the preset value, that is the number reaches the preset value 100, starting from 0, 1, 2, 3 up to 100, whatever it is, right? So when the counter reaches the set value, the contacts change their state. So this is what is the meaning of the up counters and down counters as used in the PLC scenario, right? Now after having seen this, let us try to look into some diagrams here. Maybe before that, let me look into the elements of counters. Again, before looking into the diagram, let us have an idea about what are the possible elements that a counter possesses. Counter can be considered to consist of two basic elements. One is a relay coil to count the input pulses. See, you have got a photo door here, something like this. I got a door. Okay. So now I wish to the record of the entry of the people who are coming from here, right? So maybe I have got one photo sensor attached to this door, right? So now the moment this person goes inside, right, the light rays which are being sent from the transmitter to receiver, they are cut a signal something like this. So as long as nobody is entering there, you would get a here something like this. But once a person enters, sorry, this is no longer going to remain as a straight line. You will get some obstacle, that is called as the change in the signal. It can be done with the help of relay coil also, as long as the PLC is concerned. But in other circumstances, other things, right, you would always have some kind of actuator or something like that, which should be able to give you the change in the state, right, which indicates the happening of some external event, maybe a person coming inside, the rotation of the shaft, or the bottles getting filled up in the crates, whatever it is, right? So depending upon the requirement. So then after that, the second one is reset the counter. So it is again, you can recall the operation of the timers, right? The timer gets activated by means of some input signal, say for 10 seconds. After the 10th second is over, the timer contacts would activate or would actuate some other output. Very similar to that, here, one to reset the counter, the associated contacts of the counter being used in some other rungs, right? So one is used in one rung, that is a relay coil or something like that. The resetting operation, right, it is taking place by virtue of another relay coil or another coil, whatever it is, right, which could be either located there itself or it could be located in some other rungs also. Generally, they are located in other rungs. So these two are the basic elements of the counters, and accordingly, let us look into these diagrams. So maybe these diagrams are visible to you clearly. Let me first take these three examples. So this is what is the representation of the counters. You can see the first diagram here. So you have RST, it is